The web seminar today is presented by the E-Extension Farm Energy Community of Practice at extension.org and the University of Nebraska-Lincoln Extension. My name is John Hay. I'm an extension educator here at the University of Nebraska. I focus on energy and biofuels and have for about 5 or 6 years here in Lincoln. We've done a number of these web seminars over about a 3-year period, and I'm very excited today to be the presenter at today's presentation, so I'm introducing myself. Many times I invite experts from other types of topics. Today I really was interested in focusing on small wind energy and wind energy and talking about some things that I've learned over the last 5 years that have really helped me in teaching other people about wind energy, as well as explaining to both kids and adults how wind turbines work, why a wind turbine is designed the way they are, and I hope that this will help you deal with answering some of those questions, doing some of that youth teaching. One of the big youth teaching pieces that I did a few years ago was the National Youth Science experiment for the National 4-H Council was Wired for Wind, and myself and another person here at University of Nebraska wrote that curriculum, and I'm very proud to be a part of that. Today's topic is going to be wind power physics and kind of the basics of wind. And we're going to get a little detail, but also kind of keep a little bit on the general side so that we can move through a lot of different topics today. You know, just here's a map of the United States. You can see that the Midwest and the Great Plains are the kind of best places in the United States for wind, and yet I like to say that there really is good wind locations in almost every state, yet some of those states, some of those best locations are offshore. So if we were looking at, for example, South Carolina, there's not a lot of very good wind sites, but there is offshore for large wind turbines. There are some locations, as well as a small wind turbine doesn't necessarily need quite as high a wind speeds to do relatively well. So let's start with some math and some physics. And we may have learned through physics that kinetic energy or the energy in moving objects is 1/2 times the mass times the velocity cubed. Well, in the case of a wind turbine, we know that that air molecules have mass. We know that because when we're outside, they can blow very hard and blow us, make it hard to walk at times. I mean, I'm from Nebraska. There's a lot of wind, and I've had to lean into the wind many times walking on campus and other places. So we know that it has mass, but at the same time, it's hard to calculate that mass because it's so many little particles. And so we're not going to calculate individual air particles, so we have to do this a little different way to look at it from a wind perspective. And in this case, what we're going to do is we're going to take a mass flow of air through a disk, and in that case, that disk is going to be the size of our wind turbine. And so if I take that mass flow and that mass flow, here's what I'm talking about, here's the mass flow of air over a period, and is equal to the density of the air times the swept area times the velocity. And so that's pretty simple part of that equation. And then what we're going to do is simply add that part of the equation in for replacing m, and in doing so, we're going to change our equation by adding the density of air, the swept area times velocity in for m. Then we come up with the equation down here of the power in the wind, or the kinetic energy, is equal to 1/2 times the density of air times the swept area times the velocity cubed. And this is a really important equation. Knowing how to use it, for you may not be real important, but knowing the pieces of it and why each piece is important, I think can really help explain how wind turbines work. So here, if I've kind of defined these, so V in this case is the effect of the wind speed or the velocity. The A is the swept area, and the rho is the effect of the air density. Another way to look at that, and I'm just representing some different parts of it here, and we can pay attention to one side or another, but if we're doing this in watts, here, then we're adding K. In this case, it's just 1. If we're going to want to do it in kilowatts, we have to do it use 1 over 1,000. It's just a way to look at it in the units of our choice. I like to do it in watts because 1 is real simple, then I can kind of ignore it. But the other thing that's nice about this equation is that air density for many upland sites, which a lot of these turbines are going to go in, is very close to 1 as well. So we can actually ignore in this equation both the K and the rho because they're both just 1. And so then you really only have 2 pieces of this equation which are quite easy to deal with, and that is the swept area in meters squared and the velocity in meters per second. And remember, if you're going to do the equation, we need to have our units be correct. So in this case, we need to convert everything to meters per second and the swept area to meters squared so that it all works out properly. So for the examples today, I'm going to use this wind turbine. I just wanted to show you a picture of it, and I did use this turbine only because it's relatively common. It's been around for a long time. The Berge out of Norman, Oklahoma makes this turbine, and they call it the Berge XL1, and its initial rating was 1 kW. When they started selling them, there was a 1 kW rating. I haven't looked up the rating today. The rating today could be a little different because they rate them differently today than they did. So let's just graph that equation. If we graph that equation, then we've got the representation of this. So we have the wind speed on the x-axis and the wind power on the y. And why this is really important is you can see this cubic relationship of V cubed here, and V cubed and what's happening. Because we have a cubic relationship, the velocity is really, really important to the wind speed. So let's just give an example. So let's say somebody says, I have this great wind turbine. It's this new state-of-the-art design, and this wind turbine is better because it can actually create power at wind speeds below where others can't create power. So it can create power when the wind is only 2 miles an hour. And I think from a physics standpoint that it can create power when the wind is 2 miles an hour, so there is almost no power in that wind, and so it can turn almost no power into almost no power. So excellent. I can create very little into very little, and in the end, I have very little energy. So I'm not convinced by that argument. I think to myself that the laws of physics say that there's almost no power in that wind, and so I can turn that into almost no power. I don't really care. And so that turbine, if it doesn't start spinning until the wind is 7, 8 miles an hour, all of a sudden, that's where I'm starting to gain the amount of power that I have. Now, another note on ratings of wind turbines. If this is in the old rating system, this is rated at a 1 kW turbine, and at that time, I have to have about a 17, 18 mile per hour wind to get that 1 kW rating. Well, really, my average wind speed is closer, in most locations, is probably in the range of maybe 8 to 12, and so really, it's only creating about half of that energy. A way to look at that, another way to look at that is if I have a wind speed that is 2 miles an hour, and I can say 2 times 2 times 2 because I have a cubic relationship, 2 times 2 times 2 is 8. Great, 8. If I have a 10 mile an hour wind here, 10 times 10 times 10 is 1,000. And so you can really see that cubic relationship is really, really important to wind, to how much power is there. So don't be worried about a turbine that does not spin at low wind speeds. There's no power at those low wind speeds, or very little. So we have to think about on a turbine, what can we affect? How do we affect how much power we can that there is? Well, we can't affect we can't affect the air density, things like that. But what we can affect is things like the swept area. So in this case, the swept area, we can affect the swept area by having a bigger turbine. Larger turbines or bigger swept areas are going to be able to catch more of that air because they are larger. And so this is also a reason when somebody will say, well, I've got this great new turbine and it's about 3 feet across, it's going to create all kinds of power. It's going to power my home. Well, not likely because it's only 3 feet across. And if I can only catch that much wind, there's no way I can catch more wind than how big around that is. So I can say, no, I don't think it's going to power as much as you think because its swept area isn't very big. A lot of turbines that are going to be the size to power a home are going to be in the size of this 8 to 12 foot swept area if you're going to power a home. In the case of a large wind turbine, that 8 to 12 foot is going to be more, the large wind turbines are going to be more like 100, 300 feet at times across. So if you can imagine 300 is as tall as a football field, so that would be a large wind turbine. These are all very small wind turbines comparatively. So we're going to look at some other things that we can affect. Obviously, the velocity is something that you don't really think you can affect because, we cannot affect how much the wind blows. But what we can do is affect where a wind turbine is placed and how high it is placed. And so in this case, putting a wind turbine in a good location is important, but also then getting it off of the ground is very important. Because of this cubic relationship, the difference between something that's 30 feet off the ground and something that's 60 feet off the ground is actually a 41% increase in power. So the difference between this one and this one is a 41% increase in power. So I can really get more out of my wind turbine by getting it off the ground. This is another reason to say that if you want to put a wind turbine on top of a house or something like that, one of the reasons that's not a good idea, there's more than one reason, but one of the reasons that's not a good idea is it's low to the ground and there's not much wind low to the ground, and thus you're automatically hurting that or putting that turbine at a disadvantage. We know how much power is in the wind by the wind speed, but at the same time, the second law of thermodynamics tells us that there is no way that we can catch 100% of that. Nothing, when you convert energy or power from one form to another, there is no way to catch one, for that to be 100% efficient. And so, when what we're doing is taking energy that's movement in the air and turning that into rotational energy, and then actually in turn turning that rotational energy into electrical energy. Well, even on the rotational energy side, there's no way that really we can catch more than about 60% of that. So Albert Betts in 1919 calculated that the limit is about 59.3%. So when we talk about efficiency of wind turbines, if we're using the term efficiency properly, it should never be more than 59% efficient. If they say it's more than 59% efficient, likely that's not true, or they're not using the term efficiency properly. So again, I'm going to throw this out there. In this case, I've got the power and the wind as my red line, and then I've got the Betts limit. So I know that this is how much energy or power is in the wind, but then I cannot catch more than the blue line amount. So again, if I'm looking at that wind turbine, remember that 1 kilowatt rating, I said 17 miles an hour. Well, I can't catch that much. So now actually the reality is it's got to be in this range where it's got to be over maybe closer to 20 miles an hour. And actually when we show you actually how much it can catch, which I have those numbers following up, that number is going to be out here. So its rating is on a very, very fast wind. And so the reality is that's why we're starting to rate these turbines differently as far as having a rating. There are three different types of turbines predominantly, and they are going to have different efficiencies because they have different designs. Now, turbines look many, many different ways, but we can really bring all of them back to these three general types. The Savonius turbine is a predominantly drag machine, and you can see that it has very high solidity, and in this case, the wind may hit it going in a right to left direction and spin it in this way, but also the wind could come in the other direction and still spin it. So the wind can come from any direction. The same with the Darius, wind can come from any direction, but it's different in the fact that it has airfoils for blades. This does not have airfoils for blades, thus it's predominantly a drag machine. This has airfoils, thus it has a lot of lift and a little bit of drag. And those lift forces cause that to be able to spin much faster than this type of machine. The horizontal axis turbine, similar to the Darius, has airfoil blades, and those airfoil blades cause that to be able to spin much faster. And we'll talk about some of the pros and cons of these different designs. One thing we want to get to quick is the tip speed ratio of a wind turbine and its effect on the efficiency. The tip speed ratio is simply, if we can think of it, the ratio of the speed of the tip of the blade. As that tip of the blade spins, what is the ratio of that compared to the wind speed? And so if we think about, we go back and we think about this type of turbine, it really can't spin much faster than the wind blows. And so it has a little bit of, its tip speed ratio is at or under 1. When you have lift forces, the tip speed ratio can be much higher. And so your tip speed ratio can be 3, 4, even 6, 7 to 1, where it can spin much faster. So if you think about this, the tip of this, as it spins at a couple hundred RPMs at times, it's spinning at maybe 100, 120 miles an hour, while the wind hitting it might only be 20 to 30 miles an hour. And again, you're seeing that tip speed ratio of 4 to 6. As you increase tip speed ratio, your efficiency begins to approach. As you get to a tip speed ratio of 7.5 to 10, your efficiency begins to approach the best limit. And so if you think about the Savonius turbine having a tip speed ratio of 1, its efficiency cannot even begin to get close to the best limit. So your efficiency is very low. So they're inherently not efficient machines. So again, the Savonius turbine is primarily drag. They have seen power coefficients or efficiencies as high as 30%, but that's not very typical. You're typically in that 10% range, so they're not real efficient machines. Again, tip speed ratio of less than 1. For the Darius and horizontal axis turbines, we can see tip speed ratios of 7 to 10, and so we have efficiencies that are closer to the BETS limit. Here's a graphical representation of that. And again, when we talk about efficiency, this is an important piece. What we're talking about is the actual production of that turbine divided by the energy in the wind. You can recognize this equation from the beginning of the power in the wind, actually. So we have the actual power produced over how much is in the wind hitting it. And so we can see that Savonius turbines tend to be relatively inefficient, are on the lower side of this efficiency. We have efficiency on the y-axis. And so here's the American multi-blade windmill, or maybe sometimes we call it a Chicago style, or also a water pumping windmill. So it's, again, got a little bit of lift forces, but a lot of drag forces, and so it's on the lower side of the efficiency. The Darius and the modern 2- and 3-blade turbines are getting up there where they're in that above, or the Darius at times can get up in here as well, above 0.4, 0.5, or 50% efficiency. Again, as we get up closer to this is where that theoretical maximum is. So we're doing pretty well with the modern high-speed windmills. If you think about a large wind turbine, they seem to be turning very slow, but the tip of that blade is going in the 130 to 170 mile per hour range. We have a question: what is economical efficiency of wind turbines? Again, economical efficiency is, as we talk about efficiency from a physics standpoint, efficiency is not necessarily the best thing to think about when it comes to economics. What really determines economics in a lot of ways is what is the cost of the turbine. If the cost of the turbine is relatively inexpensive, even if it has relatively low efficiency, it could be economical, because the fact is that the wind that's hitting it is free. There's not any cost in that. So again, it really depends on the cost of the turbine. Though at the same time, we know that turbines are relatively expensive. So if they're relatively expensive, the higher the efficiency, the closer we are to being economical. And so obviously, these types of turbines that have higher efficiency are going to produce more power for the same cost, if we think that the costs are similar in making different types. And that is somewhat true. because materials, even though we make them in a different design, materials have that similar cost. So again, cost of the turbine. We'll do some economics at the end that will show some of this. Okay, let's talk a little bit more about efficiency for a moment. One of the reasons that efficiency is lower in some turbines is if we can think about the wind moving in and hitting our turbine blades and causing those turbine blades to spin, there is some turbulence being caused by those turbine blades and causing the wind behind that, which basically is the same wind, but it imparts some rotation to that wind. And it's been shown that the faster that this turbine blade spins, the less rotation is imparted into the wind behind it. And thus, they have less losses from what we call wake rotation, or causing that, putting energy into that. So more energy is being taken by the blades, less being put into spinning the wind behind it. So we can see this is basically an explanation of why a higher tip speed ratio has higher efficiency. Let's move on a little bit. I just want to touch on overspeed protection a little bit, because all wind turbines have some type of overspeed protection. Basically, they have to have a way to protect themselves against high winds. We know that the average wind speed in many areas may be 9 to 12 miles an hour, but we also know that there are some extreme events. And I'm not just talking about tornadoes, but other high-speed events. And we see high-speed events in Nebraska periodically, once a year, twice a year, that might hit in that 60 to 70 mile per hour range, and at extreme times up to 100 mile per hour straight line winds. And can that turbine survive that? And if it is always, it has to have a way to deal with that amount of energy. One way to do that is side furling. And I think side furling is an interesting and neat way. It's kind of the old-fashioned way. This is how the Chicago-style windmills, or the ones that are pumping water, deal with overspeed protection, as well as how a lot of turbines with tails deal with that. And what they do is, if you can see here, this turbine is offset from center off of this pole. And by offsetting that a little bit, what happens is that when the wind speed gets very high, more wind is basically hitting on this side of the pole, the right side of the pole, than on the left. And when the energy hitting that, or the power hitting that, overcomes the spring tension in a spring that is in the tail, all of a sudden it turns sideways to the wind, and when it's sideways to the wind, it sees much less wind, and thus the speed of the blades slow down a little bit, and it's some protection. In this case, they're saying that the weight of the tail is a little bit of that. It's overcoming the weight of the tail to bring that up. Sometimes it's a spring. In this case, they're showing the weight of the tail. And so we've got that as one type of overspeed protection. Other types of overspeed protection could be just in the design of the blades and how we pitch those blades. The blade pitch angle is how we pitch them into the wind, and also the wind speed hitting them at different angles will act differently. And so some of those turbines, as the wind speed increases, they start to see turbulent airflow behind the airfoil at certain wind speeds, and what that does is basically loses some of that energy by causing turbulence, and we call that aerodynamic stall. And so that's a common way to reduce the rotation of those blades, by losing that energy. If we think about a large wind turbine, they can actually pitch their blades to either go through aerodynamic stall or just to lose efficiency to try to slow themselves down on an ongoing basis. Small wind turbines have to basically design it so that at a specific wind speed this happens, or they have some type of passive pitch system that causes the pitch to change as the speed increases. Vertical axis wind turbines like the Savonius and the Darius can see wind from any direction, and because of that, they can't furl. Also, they tend to be fixed pitch, so they have trouble changing the pitch of that blade, so having that aerodynamic stall feature is difficult. So basically what I'm trying to say here is that vertical axis wind turbines tend to have less options when it comes to overspeed protection. Your options tend to be an oversized generator or a brake, both are which are in some ways more complicated than the passive technologies that I just showed in aerodynamic stall and furling. It's not to say that horizontal axis turbines don't have difficulty in overspeed protection. Overspeed protection is a challenge for all turbines, but there's just not as many options when it comes to a vertical axis turbine. And that's one reason that has kind of explained some of that and the efficiencies and other things I was talking about, kind of explains why the horizontal axis wind turbines have become the predominant turbine design. Let's talk about that Berge XL1 again, and every wind turbine that you're going to be able to purchase hopefully has some type of a power curve, and hopefully that power curve was not just drawn, it was actually done in testing. And so here's a power curve that says this is how much power this will create at different wind speeds. And you can see here that at about 32 miles an hour that our power dumps. And that happens because of the overspeed protection of that turbine. Basically, at this point right here, that turbine began to furl, and when it furled, it's not seeing as much wind. It's still creating some power, almost like but by furling, it almost acts like it's seeing about a 16 mile an hour wind when actually it's seeing a 36 mile an hour wind. So it really does help, and so that's a pretty effective overspeed protection for that particular turbine. If we were to take that example power curve and put it onto our chart of power, so both, again, power in the wind, the Betz limit, what we can do, and the actual turbine, we can see that turbine at parts of at different times is fairly close to the Betz limit. It's doing pretty well as far as efficiency. And then as it gets higher, faster and faster speeds, and finally begins to furl, it's a little further away from the Betz limit. But I think what's neat about that is in its real range where we're seeing a lot of winds, it's doing pretty well as far as how much power it produces. But again, this is one where we can say that if this is a 1 kW turbine, so at what point does it hit 1 kW? Somewhere in that 20 to 25 mile per hour range. So it's rated at a fairly fast wind speed. Today, a lot of turbines are rated at 11 meters per second, which is faster than miles per hour. But again, this wouldn't be a 1 kW turbine if it was rated by the Small Wind Certification Council today. But that doesn't mean that it's not a good turbine. It's just rating would change to be a little different. All right, let's talk about the wind resource and how much wind is in your area. If you have taken much statistics in your time, which you may or may not, you might have heard of the normal distribution or a bell curve. In the case of wind, we have the Rayleigh and the Weibull distribution, and I'm just going to show you a Weibull distribution here, which says that this is the wind speed on the x-axis and basically the percent of the year on the y-axis, and this says that very, very small amount of the time is there no wind, and very small amount of the time there's wind over 20 meters per second. But quite a bit of the year, there's wind in this 4 to 8 meters per second range. And you can think of it kind of like a bell curve or a normal distribution, but basically says this is how much of the year at what wind speed. So let's actually look at a real one. Here's one for Lincoln, Nebraska. We got this data from the High Plains Climate Center. And we can see that Weibull distribution is actually pretty accurate, where we're seeing this kind of almost a bell curve, where very little of the time is it above 20 miles per hour, and not much of the time as you can imagine this going down here, not much of the time is it 0 miles an hour. And so this is the percent of the year and the miles per hour blocks. And so if we were to take that and apply our power curve to it, we could actually say that at that 0 to 5 mile an hour, remember our power curve says our turbine's not even spinning. But again, we don't really care because there's not much power in the wind down here at 0 to 5 miles an hour. And so then we can say hours per year. There's 3,000 hours per year where it's 5 to 10 miles an hour. And this is about what it'll produce at that wind speed. We have 1,700 hours a year where it's 10 to 15 miles an hour, and it'll produce about 0.42 kilowatts at that time. Again, now we're getting into some higher wind speeds. We're producing a lot more, but there's not as many hours that we're producing that. And again, above 20, boy, we can produce a lot, 1.5 kW, but only for 146 hours a year. So we can look at that. Now, if we were to multiply these together, we could actually try to estimate how much this turbine might create in a year. This is one way to estimate it. There are other ways. And this is what we come up with, is that we are getting 500 kilowatt hours from the 5 to 10 mile per hour block, 700 kilowatt hours from the 10 to 15 block, and so on. And so we can see that really this is our bread and butter right here, where 10 to 15 miles an hour. And if we were seeing an average wind speed of 12, which is one of the sites that I have a wind turbine at is 12 miles per hour, that fits pretty well. So there's a good number of hours, plus we're getting a good amount of power. Again, out at that higher wind speed, the problem out here is I just don't have a lot of numbers of hours, even though I'm creating a lot of power at that time. So again, it gives me an estimate of 2,077 kilowatt hours per year for that particular turbine. We can see that different places in the state have different distributions. Some of them fit that Weibull distribution a little better, but there's other ways to scale that Weibull distribution so it fits these a little differently. But again, we can see that if that 10 to 15 miles per hour is our bread and butter, then this has about almost 25% of the year at that wind speed. This location has about 20% of the year at that wind speed, and this location has about 15% of the year at that wind speed. So we can see that maybe the best location for this turbine in this sense might be our Concord, which is in northeast Nebraska, Lincoln's in eastern Nebraska, southeast Nebraska, and Scotts Bluffs in western Nebraska. Just a representation of efficiency here. I want to explain one thing that sometimes I think gets confusing, and that is when we talk about efficiency, efficiency is simply the energy out divided by the energy in. So we can think about that as actual production over the amount that is hitting it. If we think about this, the other number that we sometimes see, and people equate it to efficiency, but it's not, is capacity factor. And capacity factor, one way that I like to describe it is what percentage of the year is that turbine running at its rated power is one way to look at it. And so basically it's actual production over the max, basically if it was running over at its rated production all the time, which we know is not possible, but this gives us a number that we can look at. So if we were looking at this particular turbine based on the estimates that we have, we might say 2,000 kilowatt hours divided by 1 kW times the number of hours in a year, and so we have a capacity factor of 0.24. Now, capacity factor 0.24 or 24% sounds kind of low, but again, we have to know what's good and what's not. An example for a large wind turbine, a large wind farm, for the whole farm, a capacity factor of, let's say, 45% would be very good. While there's two wind turbines here on the north side of Lincoln have a capacity factor of about 25%. The problem with those two is, well, one is put in a better wind location than another. So your wind location has a lot to do with that. Your turbine itself has a little bit less to do with it. The reason your turbine might have an influence on capacity factor is if you broke down. If you broke down, that's going to make you run less of the year, thus you're going to have a lower capacity factor. We're seeing some of the new wind farms that are put up in Nebraska in some very good locations in their first part of the year that they're running have capacity factors in the 60% range, which is phenomenal. And part of that is they're brand new, so they're not breaking down, they're functioning very well, but also they're being put in a place that has very high and consistent wind speeds. Okay, things that affect capacity factor, winds that are different than the rated wind speed, Again, so if you have a slower than rated wind speed, you're going to produce less power, so your capacity factor will be lower. Downtime for operation and maintenance, or winds below cut-in or above cut-out. You may have extremely high winds that are the wind turbine is shut off, or basically it's overspeed protection have kicked in, and those don't help your capacity factor. Things that affect efficiency, obviously, the blade's ability to catch the wind, your design has a lot to do with efficiency, the generator efficiency, and then inverter efficiency. So if we're looking at overall efficiency of that turbine, there's lots of different parts. If it's small wind turbines have inverters, and those all efficiencies are going to affect the overall efficiency of the system. Let's just talk briefly a bit about small wind turbines and the power actually getting onto the grid or getting into your house. Small wind turbines tend to create wild AC power or some other type of relatively uncontrolled electricity, depending on how they're designed. Many of them create wild AC. I can't put wild AC into my house. I need to have in-phase AC power. So I put that through an inverter. This is my picture of inverter. It takes AC power to DC and then back to clean in-phase AC power, which then I can use in my home or put on the grid. Some people have told me at different times, well, my local utility won't buy the power from my turbine. Well, the reality is that's not true. Nationwide, there is some federal policies like the Public Utility Regulatory Policies Act and others that say that they have to purchase that power from you if certain things certain requirements are met. The reality, though, is they do not have to purchase that power from you at greater than their avoided cost. Avoided cost, in this case here, is basically the utility's cost to generate that electricity. So they don't have to pay any more than what it costs for them to generate electricity. So in Nebraska, that might be fairly low, between 2 and 3 cents. Actually, one utility in Nebraska has said that they'll pay 4 cents right now. But again, that's much less than the retail cost of what you buy electricity for, which might be 7 to 10 cents if you're in Nebraska, and if you're in eastern states, it might be 10 to maybe 18 cents. And so I think what they mean by they won't buy the power is they won't buy it at retail cost, which is true for many utilities. They aren't going to buy that for retail cost. But federally, they have to hook you up and let you put that power on the grid. That's a federal law. Now, there are many states that are adopting regulations and laws that we call net metering. And basically, there's different ways to describe it, but one way is to say that you're being able to take advantage of some of the electricity that you're producing, you're getting credit for at full retail rate. To read this, it's an electricity policy for consumers who own generally small renewable facilities such as wind, solar, etc. Net in this context is used in the sense of meaning what remains after deductions. In this case, the deduction of any energy outflow from the metering energy inflows. Under net metering, a system owner receives retail credit for at least a portion of the electricity they generate. Now, I think net metering is kind of confusing at times, so we're going to talk about it a little bit more. Here is my little chart that is not net metering. So this is one that is actually not net metering, and what we've got is that our wind turbine is creating some electricity here, spinning. That electricity is being run through a meter so we can measure it, and then it's going onto the grid, and the utility is paying us avoided costs for that power. At the same time, here's my house. I am purchasing power from the grid at retail rate and using that for my house. So my wind turbine is not actually connected to my house in this sense. It's just being connected to the grid. And this is the way that these were installed. In particular, 5 to 10 years ago, this was a very common way to put it together. It still at times can be a way to go, but again, you're not getting paid as much. This might be 3 cents this might be 10 cents, you're actually not getting very much for your power. A little better way to go, but still not net metering, is that we simply create that electricity and we run it through our house first, so that any electricity that we are using in our house at that time gets used. The excess goes to avoided cost, and then if we actually need more power, we are getting that off of the grid at retail rate. And I call that the use it first system, and it's another way to set that up. Here's our net metering situation where, again, we're using that power first, and basically then we're getting credit for that at retail rate. If we have excess, it goes onto the grid, but the company is keeping track of how much that is, either by a second meter or, in this case, by our meter running, stopping running or running backwards. And then if we need any power, we're not producing enough at any one time, we're purchasing that from them, with the difference being at retail rate. But if we created more, then we can go against our kind of our credit for that. Now, in Nebraska, that credit is only calculated on a monthly basis. Other states do that differently. So in Nebraska, net metering has a couple of things in our particular law. We can only go to true net metering if we're under a 25 kW capacity, so it's only for small systems, which actually is fine for most small wind turbine systems. Where this might be a little low is if we had a system like a methane digester or something like that on a farm, where that wouldn't be quite big enough. But most wind and solar systems, 25 kW would be more than enough to run a house. Electricity produced during the month can offset electricity consumed on the premises during that month. So excess credit to the bill at avoided cost during the month. Excess at the end of the year is paid out to the customer. We basically, at the end of every month, we stop, but then at the end of the year, if we've produced excess, they'll pay. And then there is some limits. The utilities, if there gets to be a lot of wind turbines in a particular utility, they don't have to do net metering if over 1% of their monthly peak is reached. That's not likely going to happen, but is in that law. Here's a bunch of states that have net metering policies. You can see that only a small number don't have net metering policies. South Dakota, Tennessee, Alabama, Georgia are really the only, or actually that's Alabama and Mississippi, don't have net metering policies. Every other state has some type of net metering policy, and you can see the numbers. The numbers basically represent the limit on size, and some of those limits are are different for investor-owned utilities and public utilities and other things. You can see that in Colorado there is no limit. In Iowa it's 500. Nebraska it's 25. In New Hampshire it's 100 kW. Connecticut it's 2,000. But then there's also, the STAR says there's some other state policies. So a lot of them have that net metering policy. Net metering is definitely a benefit for the producer or basically the wind turbine owner, because it allows you to get more of that at retail rate. And so let's just look at our house. And so here's our house in one day. And so this is what we're consuming. So at night, I'm not using much energy, electricity. I wake up in the morning. If it's my house, I turn my coffee pot on, I cook my oatmeal, and I cook the waffle for my daughter, and I'm using a bunch of electricity, plus the heat is on and other things, and so I use some electricity. Then I go to work, then I come home, and I cook dinner and other things, and so here's my kind of daily use. At the same time, my wind turbine might have a little different idea on when it wants to run. So here's my wind turbine, and it's doing pretty well at night, but in the morning it's not producing very much, and then during the day I got some wind, and then again, so this is just kind of what might happen on a day. In a not net metering situation, basically I'm putting these pieces of electricity, this amount of electricity on the grid, here, 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 and here, and I'm only getting a paid avoided cost. On a net metering situation, I'm still putting these on the grid, but but I'm getting credit for those on my bill, basically, that I then can use to eat up some of this time when I'm consuming more than I produce. Okay? So another way to look at that is to say that if I were to do this on a cumulative basis, so this would be cumulative consumption over a month, is that I am using electricity more and more, I'm producing it, but I really only care about what happens to this number here at the end of the month. And in this case, I would say that I use more than I produced, but my bill is actually only this much. In a situation where I actually produce more, I have where my bill might be theoretically zero because I produce more. I might have some standard charges, but my bill is for electricity is nothing. And actually, the utility owes me, but in Nebraska, they're only going to pay me avoided costs. Remember, this is 1 month. And if I'm in another state, like Iowa, for example, I might, at the end of each month, I'm actually just going to put a credit. And so in this case, my wind production is high in the winter months. I'm actually just going to pass this credit on to the next month. And so what's nice about passing that credit on to the next month is that then in the summertime, when I'm using a lot more electricity, I can just start to eat away at these credits. And so basically at the end of the year then is what I'm caring about. So I did this little thing. I'm not going to try to explain this in great detail, but basically what I have is consumption, production over a year period for a fictitious house, and then three different net metering policies, and what would I pay. So I have Nebraska's net metering policy, Iowa's net metering policy, and no net metering policy. And to explain this in the end is that if I had Nebraska's net metering policy and I had these numbers, I would end up paying $111 for electricity total for the year. In Iowa, I would only pay $48. Because I was able to pass those credits on into those summer months, I ended up offsetting some of those costs, and I paid $48. If I had no net metering, I had the same wind turbine, so basically I'm on a use-it-first situation. I wasn't able to, I would get I'd pay about $306. So you can see that there is absolutely a benefit to any net metering policy, whether it's monthly or an annual net metering policy like Iowa's. And I have some of my assumptions down here in the corner. But you can see that annual is a benefit over the monthly, but at the same time, any net metering policy is better than no net metering policy. Let's just briefly talk about incentives. There's incentives for small renewable systems. There's 3 incentives. There's the federal tax credit, which everybody qualifies for, the USDA REAP grant, which rural businesses and farms qualify for, and then net metering, which if you're in a state that allows net metering, you qualify for. The federal tax credit is 30%. That's 30% as a credit off your tax, so you have to have a tax burden to be able to take that. But one nice thing is that you can take it over more than 1 year. The REAP grant, remember, the only qualify if you're a farmer, rancher, or small business. Actually, if we're in the state of Nebraska, rural business means anybody that is outside of Lincoln or Omaha, or Grand Island, because those are the only urban areas in the state. Anything outside of that, if you're even in a town of 20,000 or more, that's still considered rural, so you qualify. Now, I want to make one thing very clear on this USDA Rural Energy for America program grant, and that is that you have to connect it to a farm or business load. And what I mean by farm or business load is that I have to connect that to a meter that is solely for that farm or rural business. So if I'm on a farm and I want to connect that to my farmstead, if my house is also on that same meter, that's not going to qualify. But if the house is on a separate meter, then I can put it on my farm meter and it can qualify for that grant. And that's up to 25% of the project costs, and so that's pretty significant. So just to review, again, federal tax credit 30%, USDA REAP grant can be 25%, and that net metering, basically which allows you to receive full value for some or all of the electricity that you produce. Let's just talk briefly about turbine siting, and then I'm going to finish up here. When we put things low to the ground, turbulent winds cause problems, and so this is reason number 2 for not putting things on top of a building or something like that, as you cause turbulent wind. There's turbulent winds, and so if we're going to place a wind turbine, we really need to place it above the turbulent winds, and that can be as much as 20 times the height of an obstruction away from the obstruction and 2 times the height. So if I think about a windbreak or something like that, I need to be significantly over that windbreak or significantly far away from it to be able to deal with that. Okay, here's what I know everybody's excited about. People are excited about small wind turbines and putting them on buildings. And I am absolutely not excited about small wind turbines and putting them on buildings because of the 2 of the reasons I already showed, which is there's low wind speeds, so you don't produce much power at low off the ground, and number 2, you have turbulent winds, which are slower and, again, not producing much power. So let's just give some examples. I like examples. Here is a Savonius type of wind turbine put on a building in Lincoln, Nebraska. These turbines were partially paid for by a grant from a local utility, and so I called up them and said, I would like to have some data from these turbines. And they said, sure, no problem, we will get that data. That was 3 years ago. 6 months after I first called, I called again. Yeah, we'll get that data as soon as we get some. I called a year later. I called a year and a half later, and then finally, right at about 3 years later, I called them about 6 months ago, and I said, I would really love to have some of that data. And the person finally contacted me back, and he says, to be honest, John, they have effectively produced no power. I will repeat, these 2 turbines have been up for 3 years in Lincoln, Nebraska, and have effectively produced no power. The reason that they have effectively produced no power is manyfold. Number 1, they're very low to the ground. Number 2, they're on a building, so there's turbulent winds. Number 3, they are of a Savonius design, so they tend to have very low efficiency, so we aren't expecting them to produce a lot of power. And then finally, one of the most important pieces to putting a turbine on a building is that when they spin, they create vibration, and the people inside are annoyed. And so actually for a period of life of these turbines were tied down and not even functioning. And this is actually a common occurrence for turbines put on buildings, is the vibrations that they cause because of their spinning is annoying in the building. And that has been common through turbines that have been put across the United States and in Europe. Warwick wind trials proved that very clearly when they were putting some on apartment complexes in England, that the spinning was very annoying to people, thus they turned them off. Here's some that were in Portland, Oregon. Again, here's just a little evidence that the winds are turbulent, is that actually 3 of these 4 were spinning, and they're facing 3 different directions. The turbulent winds are not helping them at all. I took all of these pictures. Here's one in Thunder Bay, Ontario. I took this past summer. And again, I'm not criticizing any turbines as much as I am. Here you've got a turbine that is low to the ground, is next to a building. Likely it's not going to produce a lot. The other thing I know is that it's only about 4 foot across. It's not very big. So the reality is it really can't produce a lot of power. Here's a horizontal axis Darius machine. So here's one machine, here's a second, a Darius machine. Again, here's the problem. We're low to the ground. We've got turbulent winds because look at all these trees. And then look, we've actually got a turbine here that's put away from the building, somewhat above the trees. Actually, this one might be a reasonable application. I'd actually like it a little further away from these trees. But again, of these 3, this one is a relatively reasonable setup. It's up off the ground where there's wind, it's away from the building, and yet here we've got 2 that likely are not going to do real well just because of what they are and where they are. Here's some good applications that I wanted to show you, and we'll just show you a couple of those where, again, good applications tend to be ones where they're up off the ground, away from buildings, and that tends to be what they need to be. So what I have here is an Excel spreadsheet that I actually just got off of the Berge website, and I like it because it's just a simple spreadsheet, and the numbers aren't, you know, biased to them or anything because I'm going to change the numbers. So if you want to find this, you go to Berge, BERGEY.com, and then you can go through and find, it's on their technical page, and you can find that. So let's say I'm going to use this 2.4 kW turbine, this SkyStream I quoted. So I'm going to put in $23,000 as my total installed cost. My annual energy output is actually only going to be about 3,200 kWh. My cost of electricity, I'm going to put in 0.09 at 9 cents today because that's about what it is in Nebraska. My down payment is going to be 100%, so my down payment is $23,000. Basically, I'm saying I'm paying this in cash, so my interest rate doesn't matter and my loan doesn't matter. Now, I get down here to my state rebate. I'm going to say, in this case, that it's a private turbine, not on a farm, so I don't have any state rebate. My federal rebate is 30%, or no, my state is 0, my federal is 30%. And then I have these numbers. Now, where this is fun is I go across here to my graph, and I can say that I'm paying that back in, it's not saying very well, but at past 30 years. Basically, it's saying it's wearing out before I pay that back. So that's really not a good sign. So I can actually see my internal rate of return is negative. Again, not a real good sign. But I can change things that might help me a little bit, like maybe I'm able to get that grant, and I'm going to represent that grant with a rebate of 25%, even though it's not a state rebate, it's a federal grant, but that'll help. And so if I'm able to do that, then I can look at that, and I'm pushing that cash flow back down a little lower. Other things I can say is that I've operation and maintenance of 0.005 is my per kilowatt hour operation and maintenance. That's just an estimate. There is some O&M inflation. The other thing is electricity inflation is really important, and I think 2% might be a little low. So we're going to change that to 4%, and then let's just see where we get. Now we're getting that payback where it's turning around, but again, probably not before it's worn out. So here it's worn out at about 20 years. Again, am I thinking this is a good investment? Well, it's wearing out before it pays for itself. That's not real good. If we're going to do this for this 10 kW Berge, let's just do that real quick. $56,000. We're going to change this to 56. This is going to put out a lot more electricity, so 13,000 kilowatt hours, 4% inflation rate. We're still leaving my other rebates. And now let's look at a cash flow chart. And this one's doing a lot better, where it's actually paying itself off in 18 years, 2 years before it wears out. So a little better. So is wind turbine economics where it needs to be today? Probably not. But it is getting a little closer. If I'd have done this a few years ago, I couldn't ever really get it under 20 years payback. But here I did. I was able to get it under 20 years payback with a few assumptions. If we were in an area that had higher electricity costs, so let's say 15 cents like we were given that example, and we're assuming that we can net meter all of this, and in that case, you look at that 12 years. So if you're in an area with 15-cent electricity and you can get all the grants and other things, you may have what you need at a 12-year payback. So just some of that economics that we can show you.
This webinar has been brought to you by the Farm Energy Community of Practice and the University of Nebraska-Lincoln Extension. For more information, go to farmenergymedia.extension.org.